Hi, Junie. Thank you for joining. Can you hear me? Cash, can you hear me?
Yes, I can hear you.
Perfect, thank you. Hey,
Hello.
Moshiko.
Hey. Morning.
Morning. Thank you for joining us. We usually give people a couple of minutes, so we wait till 8:03 to get started.
No problem. June is also here, I can see. So
Yes.
it's good.
Thank you.
Great.
Thank you.
Yes. Sure.
Hey, Cliff. Good to see you.
Thanks, Anu. Same here.
You're back in town.
Back in town and back at my desk.
We'll see how long that lasts. You're traveling before you know it.
End of September, have to go to Dallas for 2 days.
Okay. Dallas is, it seems so easy compared to the other amount of traveling you've been doing between APAC and EMEA.
Yeah. Yeah, surprisingly, Dallas from Ottawa is not an easy hop. It takes 2 stops and another
Oh,
day over. It's much easier for me to go to San Francisco.
which you will be in October.
That's right.
Okay, we are 3 minutes past the top of the hour, so let's get started. I'm sure people will join in. Since Cliff is back in town, I would like to ask Cliff to reflect on the APAC summit. And then I think very importantly, what impact does that APAC summit have on the global summit? Shaping the program or changing things, given the APAC region is of so much importance to the world in general. So
Yeah, well, thank you, Anu. Many of you probably heard that we did have a very large success for our first event in Taiwan. And we already committed to go back next year. So for those that want to think about going to Taiwan, Taipei City for 2026, it'll be August 11th and 12th. We will keep the same logistics for the event. It'll be a 2-day event. We did have about 1,500 people come out, which was just beyond our stretch goal, actually. And we think that next year, 3,000 would be very much possible given all the glowing feedback. The Chiplet and Advanced Packaging Day was very well attended. We had speakers from TSMC, ASE. We had some of the local folks being able to present, which was pretty good. We also met with Microtech, TSMC. We did have a chat with Synopsys, and maybe a couple of others that I'm forgetting now. Jawad is here. I think we met a few other chiplet related folks, Artilis or something, or as well. But Jawad, feel free to add anything on top of what I said. So in terms of impact, I think there's desire and potentially commitment to start a local work stream in Taiwan. Clearly, it's the center of silicon development now, and for us to try to have a first-class citizen work stream there would probably be a really good expansion of the credibility and reach of this project. In terms of Global Summit, I would like to try and bring a few of the folks to be on a panel if there's still room for that. And I know Anu and Jawad, we have a call a little bit later to discuss that. Maybe a TSMC representative, perhaps someone from E-Tree, and maybe even someone from ASE would probably be a great addition to our day at OCP Global Summit. I'll stop there. Jawad, maybe you want to talk a little bit about your impressions.
Yeah, so Cliff, I did make some comments last week, but I'll briefly repeat. So we did notice a lot of interest in the Open Chiplet Economy Day, and as everybody knows, that pretty much anything related to hardware, be it chips or racks, they all converge in Taiwan. So the attendees were very much aware of TSMC's advanced packaging technologies. And I think something is new for them, which is this concept of open collaboration, while you still may also be competing, but because the business opportunity is so large that industry has to adopt that model. And the companies that we spoke with, they generally seem to understand that. And one interesting topic that we found that industry needs some collaboration in Taiwan ecosystem is co-packaged optics and silicon photonics. So we are going to get them some support in starting a white paper and kind of like, rally around that in their time zone. So we'll be helping with some of that initial push.
Yeah. And I think, Jawad, if the work stream gets going somehow, we'll need a monthly slot for them to report out the work here on this call or something like that.
Makes sense?
Yeah, so Cliff will work today to see what we can accommodate in existing panels, which luckily we've left somewhat open-ended, precisely for this reason that the panels are the things we can actually change up, or at least bring in a little bit more different personalities into it, possibly, and especially based on the APAC. So we will do that. Thank you for that update. It's great to see this expansion in the Asia Pacific area, and interesting to see that they want to start a group. And let's talk a little bit more about it, because it's a fair amount of work that goes into it, and we want to make sure that the volunteer leads do indeed have the time to do this in parallel to their everyday jobs and life. So thank you for that update, Cliff. Any questions for Cliff and Jawad for the APAC Summit? Great. If not, we will move on to the highlight of the day, which is Cadence. Thanks to Itai, who got me connected with Moshiko at Cadence. Junie and Moshiko are here today, and they're going to talk about Cadence's thoughts and roadmap on chiplets. I think it's really important how the EDA companies position themselves, because they're such an integral part of pretty much every step of the way. architecture all the way to implementation. Good to see what Cadence thoughts are on how this evolving landscape is going to look like for them and how it impacts all of us. So Moshiko and Juni, please introduce yourselves, and you can share the screen and I will go on silent mode.
Okay, thank you, Anu. Please let me know that you see my screen.
Yes, we do.
So first of all, a small clarification, Cadence, is doing more than EDA. We are also an IP company, and specifically both Juni and I work for the Silicon Solution Group, which handles, hardware solutions for customers. So obviously we are not doing silicon products on our own. We are delivering some sort, you can call it a service to companies that want to bring or realize products on silicon. And it can go all the way, as I said, from architecture to silicon through our architecture offerings that we will touch on today, IP, EDA, and design services. So both Juni and I are part of the Silicon Solutions Group, as I said. Juni, she'll talk later. Juni, I will present you if it's okay. So Juni is our chiplet system architecture lead, and I'm leading the chiplets R&D engineering in Cadence. All right. Feel free to stop me at any point if you have questions. So as I said, we are looking at chiplets and the value that they can bring from, I would say, 4 different angles or perspectives that we can use in order to help the industry transition to design with chiplets, where we think that we can also, as a company, provide strong solutions for customers. So obviously we believe that chiplets can help a lot in cost efficiency of products for several reasons. First of all, you can design chips with, you can design products with smaller chips. They used to do more focused on specific functionality, each chiplet, and you will see it later on. We will go over our offerings, how we are kind of disaggregating a potential architecture to chiplets. The second is customization. You can build, we believe that you can build a pretty wide range of products from the same set of chiplets. And this is something that we put a lot of focus on. Of course, the optimization point may need to be decided and will have impact on that. So if you want to use the exact, let's call it a system chiplet for all 3 systems that are here on the top right picture, then it won't be necessarily optimized for all these use cases. But definitely there is an option to reuse a lot of chiplets and build different types of systems this way. I would say in much less effort than building these systems completely separately. And this goes all the way from the transistor and the hardware to software and platform reuse capabilities. Configurability is another important point that we see that can help us drive the industry to use more chiplets. This way you can move from generation N to generation N+1 by replacing only part of the chiplets on the system. This is very relevant where somebody wants to promote or improve the CPU solution without necessarily the need to refresh the entire product, especially the analog parts and the IOs, like you have to do when you are refreshing a monolithic die. And last but not least is we are driving this with our technology. So as I said, combining our EDA, IP development in Cadence, and the design services that we give, we are focusing very much on standard interfaces and protocols as a mean to enable this. Mainly ARM CSA and UCA are the things they are looking at today. We will cover it, I think, in more details later on. And we offer flexible engagement model for customers. So that's kind of our pitch on why we are entering this domain. Today we are looking at 3 types of offering that we are developing. So I'll start at the top left. We are building a platform that is a multi-chiplet platform. And we see that as you can think of it as a reference design or a prototype for what we call physical AI markets. So we see a lot of similarity in the functionalities and IPs that are needed for automotive, drones and robotics, and some of the defense applications, aerospace and defense. These have, all of them have in common a need to build a system that has strong compute and AI capabilities, but also relevant IOs and sensors and DSPs and so on. Of course, not all these products are the same. And at the end of the day, when someone wants to build a product, they will have to customize it and put just the specific IPs that they need. But we are looking to build something that is generic enough that can serve as a starting point for a company or a customer that wants to build a solution for one of these markets. There are some examples here, and we will go into some more details on this later on. This is, I would say, a very significant activity that we are working on, and our intentions are to realize this platform on silicon. Okay, so it's not just building an architecture or an RTL design and emulation, but we are bringing it all the way to tape out. And as I said, it's a prototype, so we are not branding this on silicon. The intention is that this is a valid reference design, given that it's going to be on silicon, that will allow any interested customer to build a system based on that with us. The other focus area is building chiplets that are targeted to be a companion chiplets to an existing system. This is a need or trend that we see that is emerging recently. So the main examples that I assume some of you will be familiar with are an IO chiplet, a memory chiplet, and so on. Usually disaggregating these parts from the main die, which can be, for example, very CPU centric. And this way reducing the cost by putting these PHY or IO related components on a separate die, sometimes on a former process technology, which will make it also cheaper for manufacturing. And here we are looking at this again as ability to build very flexible solutions. So, and you will see later on that we are kind of trying to bring a family of solutions. So this can be customized to a customer's need or desire. And last but not least, and this is very important, part of our strategy, and I think also relevant for the discussion here, is that we are building all our chiplet architectures and design through what we call chiplet framework, which is, let's call it a relatively standard architecture that allows us to build different type of chiplets with their custom logic, which is what you see here in red, while using a standard definition for how this chiplet communicates to the external world, which can be in like the different cases I showed, either a main die that is maybe not controlled at all or delivered by Cadence, or as part of a full chiplet platform, as I described on the physical AI. And we are doing this with some standardization on automation. I will go into more details on the physical AI and the chiplet framework in the next slides. Any questions so far?
So are you building IO hubs, or is it the IO expansion chiplet sit attached to an IO hub?
So it can be both.
Okay.
Okay.
But you're creating standard products that are IO hubs?
Yeah, so we are not creating any silicon product, as I said, right? At the end of the day, we are working with companies that want to realize things on silicon, right? By providing them our capabilities. So it's extending the existing Cadence offering also to the world of chiplet design and architecture. That's how we should look at it. And I can say, we have very different engagement. There are some companies that have, for example, disaggregating an existing reference system. They want to build an IO chiplet for it, just to disaggregate some of the IOs. Others want to build a new architecture using chiplets. It's very different, right? There are many different desires. I would say that the common thing to all of them is that they want to move from monolithic solutions to building solutions that will be based on multiple chiplets. So the physical AI platform is a architecture and design that is based on a 4 chiplets system, where the main, or the overall control of the system resides within the system chiplet that you see in the middle. So this chiplet contains most of the general purpose and IO IPs, as well as the system capabilities to control other chiplets. We are building a CPU chiplet that is attached to it, and an AI chiplet that is attached to it that serves accelerators for CPU and AI. And we have the ability to add a 4th chiplet that you can see at the bottom right, which is a custom chiplet to a customer demand. So for example, the red part of that chiplet can be a custom IP that a customer owns or drives, and so on. The idea is that with these 4 chiplets, you can build different types of configurations. So we have customers, for example, that want to enable from the same family of chiplets, as I showed earlier, multiple products ranging from a low end to a high end. So you can think of a system chiplet as also a standalone SoC. Because this is where we manage the entire system. There is a small CPU cluster there. So if you want to build a very low-end, low-cost system, you can just use the system chiplet as is without attaching any chiplet to it. You can build a system where you have the system chiplet attached to the AI chiplet. You can build a system where it is attached to the CPU chiplet, or all these chiplets all together. So it brings flexibility on that aspect. We have a lot of relative usages that can be demonstrated and also used by customers for these markets, as I mentioned earlier, the physical AI markets. And we build this in a way that is ARM CSA compliant. So it enables our customer to work with ARM CPUs, which we also use internally. One more point is that we are, as I said, architecting and designing this already, and our intentions are to tape it out. So this is going to be actual silicon that will demonstrate. Yeah, I see there's a question.
Yes, I have a question. Thank you very much for the presentation. A couple of 2 questions, actually. One of them, you're saying you're going to do silicon, but you claimed before that actually you don't do silicon. I'm guessing that your customer is going to do the silicon, right?
We are doing, you can call it a test chip, right? It's a prototype silicon.
Okay.
So it's not going to be a product, right? We defined use cases that we're going to demonstrate on this silicon. We are doing the tape out because we believe that this is the right way also to bring confidence to customers that we know and we are able to execute to it. By the way, we already taped out last year a smaller version of the system chiplet, but it was just system chiplet standalone. And we have 2 system chiplets back to back implemented on a package, and we already demonstrating this. So we have this silicon working, but this is like more complete system representation through these 4 chiplets that we are now building.
Okay, thank you. And as for the second question was in terms of the tooling provided by Cadence to facilitate this chiplet design. And
Right.
the top you say Cadence physical AI chiplet. Are you at this level focusing on the physical die size, making sure all the pins are the right size, etc.? What is the level of coverage of the tools?
If I understand your question correctly, we are obviously doing the entire thing. So first of all, we are using only EDA from Cadence, obviously, right? We are not using other solutions, but we are doing everything from the package level to the transistor level. So this work includes the 4 chiplet integration on the package, okay? So for example, we are choosing one way to implement it and integrate the chiplets, but we are testing and validating different types of package integration solutions. Because, you know, some customer can come and say, hey, I want to realize this and I want to use organic substrate, and someone else will say, I want to use silicon interposer. Okay, we need to be able to support any package integration. I will touch later about the lack of standardization, I would call it, on this part that I think we, as an industry and OCP, can greatly help here. We need to improve. But definitely we are talking here about doing everything, okay? At the end of the day, what we are planning to demonstrate after silicon is back from manufacturing is a package that has these silicon chiplets on it. I hope I answered your question.
Yeah, Judith, I have more, but I'll let you go, and maybe I have more questions at the end. Thank you.
Okay. So as I explained earlier, we defined what we call a chiplet framework. That is, what are the main ingredients that we need to build in a chiplet in order to enable, for the sake of discussion, putting any custom logic or design on a standalone chiplet. And you know, the chiplet framework was defined to have a common language, okay? Supporting both chiplet to chiplet communication and interoperability, but also system behavior and the inter-chiplet control. This framework is architected, designed, and implemented along with the unique logic of each chiplet, as I said in colored red here. The first part of this framework is the local control that each chiplet has. So this supporting, you know, the internal registers on that chiplet, clock, power, any other aspect of local control you can think of. Resets, of course. The second part is the chiplet control that supports the entire system operation. So this is where the multi-chiplet system gets into operation. So anything that you need to manage in a system of chiplets, like security, safety, debug, interrupts, and so on, these are things that you need to have, let's say, visibility across the chiplet. So obviously, and there are 2 aspects to look at it. If you're looking at a solution where we are going to architect the entire thing, like the physical AI platform that I presented, then we are able to give that horizontal solution for the chiplet control across the board, since we control the system chiplet and we are able to communicate and propagate all the needed signals and communication between the chiplets. In a sake where we will do, for example, a companion chiplet, obviously this will be more limited to what we agree with with the customer that will probably own the main die. Okay, so on these aspects, we may enable only part of the chiplet control aspects. Okay, but the idea is that we can and we plan to handle all these aspects by looking at how to build the full system. Okay, from that point of view, and I think on that we differ a bit from others that are looking at companion chiplet point of view only. And of course, the less than part of that is the actual chiplet to chiplet physical communication interface, which we enable through the UCI IP. So this is our main focus today for chiplet to chiplet communication. We are enabling this IP in many different technologies and the different versions of it, so supporting both standard packaging and advanced packaging, and we treat it as an integral part of this chiplet framework. So now we want to dive a little deeper into the chiplet framework, and I will move the presentation to Juni to describe the different aspects that we cover here from the architecture point of view. Juni?
Hello, this is Junior. I am working on the system architecture and the performance of the chiplet in the Cadence, and then very glad to join the meeting, and then virtually meeting you together and so on, and then to introduce, to have the opportunity to introduce what we have done, and then what we are doing. So as Moshi said, what we are trying to do is to incorporate as many of the voices from the customer, because we are Cadence, we are in a kind of Switzerland, and then to provide a unified interface. So the OCP is, I believe, the best place we are getting the feedback and then really realize the chiplet together. So it's like and then so what we are focusing from the Cadence is we are doing this automation, because we are calling the first bullet is about SOC cockpit, because we believe that we have to have a capability to incorporate the feedback from the OCP or other vendors or customer to make a unified standard. So we are focusing on the automation, and then this is a DNA of the Cadence, we believe. And then as of today, we are using this standard. So ARM CSA spec, this is a beta version in public, and then the BSA spec, base system architecture spec, and then the PCA spec, and then open chiplet architecture. And then we are actually communicating with IMEC very closely to also cover, to learn about their lesson, and then how we're gonna do together. And then as Moshi said, this framework includes a security system. The first part is a security system. The next one is debug, and then control, how we're gonna control the system. The NOC, a die-to-die interface UCIe, and then this is optional safety management. So this is required for some customer, and then some customer doesn't want to have it. And then this safety management is, I can explain you later in detail how we are doing it. Our approach is a little bit, maybe you may be interested in our approach. And then the central die integration package. So Moshi, can you go to the next slide? Okay. The first one is secure boot. So you can see we are calling this as SCP, and then it has as of today, we can change it according to the OCP proposal. As of today, we have a ROT root of trust, and then the system control processor. And then the root of trust, we are focusing on how we're gonna they provide the security when the package is coming through the different way. Because if we are doing the package in one shot, then we make the ROT, we can follow the conventional way. But now the chiplet is aiming to gather the third-party package, third-party chiplet, and so on. So we are defining how we're going to handle the multiple packages from the different vendor together. So that is what we are focusing on, the root of trust and the secure booting. And then the system control processor also. And then the chiplet interface, meaning that because we are combining the multiple chiplet together, so we need a interface before at the booting stage, before the UCI training. So we are using the UCI version 1.1 as of today. And then we will gonna adopt the 2.0 as when we are ready. Because of the version 0.1, UCI version 1.1, we need some light interface at the always on power domain. So we are relying on the I3C and a couple of the interface as of today. And then, of course, we have a system counter synchronization interface to make all the timer at entire chiplet as a synchronized. Ushi, can you go to the next slide? Okay. The next one is debugging, because debugging is really, still we are doing our second chip actually. And still we are learning a lot about, wow, this is this case, that case. We are finding a lot of case. For example, when we gonna system chiplet is alive and then we're gonna power down the second chiplet and then we cannot do the daisy chain at all. So that kind of lesson we are still learning. So because, and then the another one we found out from our lesson is the software, the secure software and the system control software is now being distributed across the chiplet, multiple chiplets. And then this is defining the one system. So we learned that, wow, the debugging capability of the multiple chiplet together is, we know that from the beginning is important, but it's more important than we expected. We are using the cross trigger interfaces and so on to support the multiple chiplet debugging capability to support it.
Yeah, and maybe if I can add, I think that we are trying to look at each chiplet as a subsystem, but also as a standalone silicon. So from debug and also test perspective, we want to be able to debug and test each chiplet standalone, but also as part of the system, right, Johnny? And this duality is what bringing a challenge to support also on the software side.
Okay. Yes. Can you go to next slide?
Yes.
Okay. So this is about the system control. So how we're gonna control? So as of today, we have a main primary chiplet and then the secondary chiplet as of today. And then we are defining how we're gonna control all the power and clock together. And then and then another thing is, because we have a central power clock control at the AON domain, power always domain. And then you may know that we are trying to help the customer to encapsulate their subsystem into the chiplet to enable to accelerate the chiplet process. So we are defining how we're gonna communicate with the others subsystem. So if you look at this slide, you see that custom logic in the interface IP subsystem. So we are defining the interface and then the not interface. We are defining the subsystem, how we're gonna communicate from our control logic, system control logic to the subsystem. So, but we are not defining the DU interface. We are following the ARM and then the OCP and then UCI spec to define it. Go to next slide. So the NOC. So we are in our framework, we include a basic NOC, the non-CRUD NOC from the the cadence. And then as of today, we are having the IOMMU inside of it, and then we are trying to replace into the address translation cache, but still we are using the IOMMU as of today. And then we are building the address translation cache. And then we have as of today, we have non-current and current options at the interface, but the cadence NOC is only supporting the non-current NOC. So we are partnering the other third party to support the currency. Okay, the next one is die-to-die. So this is the PHY, and the controller is from the the cadence, and then we are very proud of our UCI PHY and the controller. And then we supported protocol is CHI, is light, and DVM C2C, and then AXI C2C interfaces. And then we are also supporting the UCI multi-mode to translate the streaming interface and ACE light interface and so on at the same time. And then the interrupt, because some of the chiplet doesn't have a processor inside of it. In that case, we have to deliver the interface to the base die using the streaming interface. So we are following the ARM CSS spec and then developed our own IP to communicate with the main die using the MSI to send the MSI transaction. Okay, that is really optional. So if the customer wanna have the safety features inside of it, then we are supporting the safety management subsystem, meaning that this is we are partitioning the safety management subsystem with the safety island. So this is not a safety island, but we need to communicate the fault and then the fault delivering to the other subsystem very efficient way. So and then in addition, it is doing the board control communication with the board. So that is, so mainly it is interfacing, having the sensor interface, and then how we can aggregate the faults, and then generate the fault into the another chiplet, and then the basic function of the recovery system, but very basic. And then we are trying to have the ability to combine this safety management subsystem into the safety island. Okay, the next one. Okay, so this is my last slide. So we have been working on the chiplet for around more than 2 or 3 years. We are really focusing on this. I worked on this area more than 2.5 years, and then we are preparing second tape out. And then what we have learned until now is we as a cadence, we really want to accelerate the customers ecosystem. And then we found out that we really need interoperability. So when we define, because we are testing the chiplet to enable the customer to learn what is necessary to as a cadence to support our customer. And then what we learned is when you try to define the system, we start to partitioning the behavior. Like we define the behavior first, and then we try to partition the system. And then we learned that, wow, how we can, if we really want to do a plug and play, then we need to have some standards of the behavior first to make a system, the chiplet dream come true. And then what we did was we defined the behavior first, and then we defined the interface depending on the behavior. For example, if we need a really urgent the event between the two chiplet, then we had to define the additional event interface in addition to the standard one at the light power domain and so on. So I believe that, personally, I believe that the OCP is crucial to make really the chiplet ecosystem come true. And then what we are doing at the Cadence is we are trying to closely collaborate with the partners and industry bodies. And then what we are doing the reference platform to see what is a real bottleneck, and then what we can do to make the ecosystem happen, it really happen. And then that's why we are focusing on automation, because that is the first target is we need to shorten the chiplet TET, and then we also have to have the flexibility to adapt the lessons from the customer. Oshi, that's it.
Yeah, so are there any questions on the architecture to Juni? I have one more slide. Okay, maybe we can go through it and then ask for questions. So I'm looking at the physical integration challenges. You know, we were asked by Itai and Anu also to think about like what are the messages we want to bring to the OCP working group. So Juni presented the architectural challenges and on the physical integration side. So I would say that our main focus, as you can understand from the examples that we share, is around the 2D or 2.5D types of integrations. We are not directly driving architecture-wise stack-up dies. So we are having such engagements with customers on specific IP solutions, but in terms of the system level and the examples we are working on, we are looking at the side-by-side chiplet integrations. And as I said, we are, as a company, focused on UCI as the main physical solution for such integration. I believe that so far what we see very good industry alignment around UCIe. This is across vendors and process technologies and customers. And this is like, I believe that this kind of alignment is what can really drive standardization later on. We are still not in a completely open chiplet ecosystem, you know, environment where you can mix and match everything. We are still far from them, I think, but I think having UC as a standard solution is definitely something that will contribute to getting there. We also see, you know, the central UC working group, the driving the spec for current and next generations and keeping, you know, the standards as well as definitions of backward compatibility between new standards and previous versions, or new speeds and previous speeds is very important and will allow more options to integrate different chiplets together. The main challenges that we still see that I think that will need more focus. So one, and we hear this also from customers, one is the interoperability of UCA from different sources. So you can look at it from two angles. One is how to integrate chiplets from different vendors. For example, when the UCI is coming from different vendors, this is something that we see by definition, like theoretically should work. There are not many who have tested it thoroughly. And from what we see, companies and customers prefer today to work with a single vendor to reduce the risk of interoperability issues here. So we still have mileage to go to there. And this also goes to cross-foundry integrations. So for example, there is a very good confidence, I think also among customers, on the ability to mix and match process technologies from different chiplets, but still within the same foundry. So for example, having one chiplet from a single foundry and another chiplet from a different foundry is still something that many companies, many customers are still very concerned about. The package integration technology is also still, you know, I call it new or immature or evolving, still evolving. At the end of the day, you know, there are different package integration solutions that the different foundries and vendors enable. This is actually where we are also a customer, because we are not, we are using partners to do the package integration. We don't own this technology. but it's very, to us, is very much like foundry, right? So we are looking at it, seeing that we are working with all the foundries. Okay, so we can see that everybody is kind of working around the same types of families. So use integrating chiplets through organic substrate or through interposer like silicon or RDL. And we know that each of these has its own pros and cons, but these solutions are implemented in a very different manner between the vendors and the foundries. And this creates a lot of dependency between the required or requested UCIe solution and the valid package integration option. So for example, for some of the integrations, you will need to use a very specific UCA IP because of constraints around noise or around other aspects of physical reliability. The last challenge that I think is interesting and OCP working can definitely look at and help promote is how do we assure physical reliability in a very early design stage. I think this is something that I also hear from many customers, saying, okay, this distribution or this disaggregation of a system to chiplet looks very reasonable and it makes a lot of sense, but how do you prove that from power and noise, especially thermal wise, this solution will be reliable? Think about, we gave the ADAS example, right? Automotive companies have a lot of concerns around how this realization of these systems at the end of the day will meet the, I would say, very strict constraints that a car has. Sometimes these things are also common to aerospace and defense that will have such restrictions. And this is an area that still, we have today tools like different 3D IC tools that help us model and simulate the chiplet to chiplet interaction. But this is like, if you do it in an early design stage, you can mainly simulate the UCIe part of the system, not more than that. And this is where we see customers are concerned about the transition to chiplets from a monolithic system. Yeah, this was our last slide. So if there are any questions, I think it's going to be a good time now.
Yep, open for questions.
You go
Yogesh, if
back
you're speaking.
one slide.
Yes.
Well, I think to Juni, I think, yeah. So I think definitely we should come back to this, but go back one more if you don't mind. So this, if you guys want to have some more conversations on this, this is Raghu. I can kind of try to see what your thoughts are on this, maybe in a separate meeting.
Yeah.
So I can ping you maybe sometime in, maybe now, but I'll just ping you now, but maybe sometime in late September. I would like to see where you guys want to take this thread out here of architectural challenges and concerns.
We'll be very glad to collaborate with the OCP working group. I already joined the chiplet track. Juni is also joining that. So definitely, Raghu.
Okay, yeah. When it's a chiplet track, there are many tracks. So at
Yeah,
least...
I know. We are still learning the structure of OCP,
No,
but
fair enough. Fair enough. At least...
definitely we want to collaborate. And yeah, the intention here is that we're just going to give a glimpse into what we're doing, and obviously any area that is of interest, we can dive deeper later on.
Fantastic. Thank you.
Yep, let's connect offline, Raghu, because I think that's a much more detailed conversation. Durgesh, I thought you had a question, but we couldn't hear you.
Yes. So this is a good presentation. Is there, given you're doing at the cadence level, is there anything like your learnings on system level which you can publish so that we can use it?
Yeah, so we are working on some, you can call it some sort of a white paper, which is exposing some of the architectural concepts that we are working on. Of course, not everything, because some of these things we have proprietary data.
Yeah.
I think we can definitely think of what of this level we can share also to this working group. I will take this section with Junie to think what we can share.
Yeah, that'd be great. Thank
Yeah,
you.
we'd appreciate that, because I think what I get out of this is Cadence would offer this as a solution.
Right.
Where if, say, I as a customer from Microchip, say I want to build, I have all these, well, I have these chiplets that I want to put together a system, you would provide that central die structure.
Right, and it can go all the way. I can tell you that we have customers that today, for example, they have their secret sauce or their specialties in radar, okay? So they want to build a radar chiplet, but they want to build an entire system. They don't have the expertise in the other parts that are very important, which is like the system parts, all the peripheral IPs, the AI, the CPU, right? So they can get a lot from Cadence, complete with their ingredient, and then have a full system built around it, right?
Right. So as far as like a CPU chiplet, they would need, you would source that from outside, because you don't actually do that, right?
So we are doing the chiplets. We are sourcing the CPU IP outside. Yeah, we don't have with CPU IP. As I said, we are working very closely with ARM, right?
Okay.
So we can do it around the ARM CSS, for example. Okay, this is how we work today with ARM, definitely. And also, you know, AI. So we have an inner AI solution. We have an NPU that is developed in Cadence and is offered. But at the end of the day, each customer has different definitions and different needs, right? And whenever we are building, for example, a companion chiplet, then as I said, we will not deliver the entire system. We will just deliver that part of the system.
Okay, understood. So, yeah, no, I see how you guys are participating in this ecosystem in partnership with ARM, and it ties in very closely with the work that we are doing. The one primary difference is, you know, we want it to be compatible with Bow interfaces also.
Right.
Yeah, we're trying to make it such that anyone who uses a reasonably popular die-to-die interface on their chiplet can actually work with other chiplets if they follow sort of this path that we hope to provide in terms of a reference architecture or guidelines or a spec.
Right, and this is where we are also interested to collaborate, because we want to make sure, for example, that this physical AI reference platform that we presented, that we're already designing, is also following that spec, so it will increase the chances of any potential future integration that may be, right?
Yeah,
so it's a very common,
Sure.
and we are looking into that. As I said, you know, there are many challenges here for interoperability, and I think the work that is being done here in OCP is very important to enable that.
Absolutely, we appreciate it. And then Itai and Durgesh and Rob run the systems group, and then Raghu's doing some virtual prototyping work. So I think these are the key people to make sure that you guys are able to talk to each other, and we can have an effective collaboration. Would you be able to share the slides with us so I can upload it to the
I will
site?
share a PDF version of the slide.
Perfect. Yeah.
Hey, one more thing as we leave, Mushiko, just I'm also curious about not now, but when we meet, about the Exilium virtual channel. I think some good white paper I saw out there on test benches. Does it come in your group or a different group?
No, so we are not the EDA group. There is the verification EDA group that drives Exilium, but I will tell you that we are using and utilizing the existing EDA capabilities usually very early before they are enabled outside. So you can consider us prototyping any such capability also for the chiplets.
Okay, thanks, and we'll catch up offline. Thanks.
Sure. And thank you for the opportunity to present. It was a pleasure.
Hey, thank you so much, Moshiko and Junie. Really appreciate it. Thanks for you know, saying you wanted to collaborate with us, because that's really what we're looking for, an open framework for many people to use, no matter what kind of chiplets they have and what kind of die-to-die interface they use. So we appreciate it, and we'll make sure we connect you with the right people.
Thank you very much.
Thank you, everyone. Have a good weekend.
Thank you.
Bye.
Thanks, Itai, again.
Thanks, everyone. Thanks, Moshiko.
Thanks, Itai. Bye.
Bye bye.